For this section, we're going to talk about solving exponential and logarithmic equations. So to start off with, we have a fact that says if b to the x equals b to the y, then it must be true that x equals y. So if we have two sides of the equation equal to one another where the bases are equal, then the exponents have to be equal is what this fact is saying. So if we could manage to rewrite an equation where it has the same base on each side, then we can just set the exponents equal to one another. So for this example, we have 3 to the 2x plus 5 equals 81, and we want to find x using this fact. The important thing to note about this problem is that 81 can be rewritten as 3 to some power. If you multiply it out, 81 is 9 times 9, and 9 is 3 times 3. So that means we have 4 3's being multiplied together, so 81 is just 3 to the 4th power. And now that we have the same base on each side of the equation, we can set the exponents equal. 2x plus 5 equals 4. And now, just solving for x, we'll subtract 5 from each side to get 2x equals negative 1. Dividing each side by 2, we get x equals negative 1/2. And then you can always go through checking this. If you plug negative 1/2 back in for x, 2 times negative 1/2 would give negative 1, plus 5 would give positive 4, and 3 to the 4th power is 81. So it does end up working out after a check, and that's always a good way to go back through and make sure you got this correct. From here, we now have 16 to the x minus 2 equals 64, and we want to find x. Take a moment, pause the video, see if you can't figure this one out. Okay, so trying this together, there are multiple ways to go through this problem. There are multiple ways because, first of all, we could rewrite 16 as 2 to the 4th and 64 as 2 to the 6th. But we could also write 16 as 4 to the 2nd and 64 as 4 to the 3rd. In general, the larger you make that base number, the easier the problem will be because it'll give you smaller exponents to work with. So we're going to go ahead and use 4 as our base. So we're going to rewrite 16 as 4 squared. I'm going to go ahead and rewrite that because that's very sloppy. 4 squared, and that's being raised to the x minus 2, and that's equal to 64 is 4 to the 3rd. From here, whenever we raise an exponent to another exponent, we just multiply the exponents together, so we're just distributing this 2 to this x and this negative 2. So we get 4 to the 2x minus 4 equals 4 to the 3rd. And finally, we now have the same base on each side, so we can get rid of the 4's, just giving us 2x minus 4 equals 3. We'll add 4 to each side of the equation, which gives us 2x equals 7. And dividing each side by 2, we get x equals 7/2. And again, you could go through a quick check of this. 7/2 minus 2 would give you 3/2. And then if you take that step by step, 16 to the 3/2 means you're taking the square root of 16, which is 4, and then raising it to the 3rd. which is 64. So again, it checks out. Okay, from here, we'll now introduce the next type of exponential equation we can solve. So to solve an exponential equation that looks something of the form a equals b to the x, your first step is to isolate the exponential expression b to the x. From here, you take log base b of each side of the equation. Remember, we do this because log base b of b to the x is just x. It'll cancel out that base b. And then finally, we just simplify to find x. So, in this problem, we have 10 to the x plus 3 equals 5. So we're going to go ahead and solve this for its exact value. When we say find the exact value, it means we're not approximating, we're not finding a decimal value. Remember to only find a decimal value if the problem specifically states that you can approximate these things. So the first thing that we should do here is subtract 3 from each side of the equation so that we can get the exponential expression, so we can get the exponential expression isolated. So that'll give us 10 to the x equals 2. And now from here, we need to get rid of this base 10. So we need to take log base 10 of each side of the equation. Remember though, log base 10 is just log. We don't write the base 10. So we're taking log of 10 to the x, and we're setting that equal to log of 2. And now log of 10 cancels out, leaving us with just x equals log of 2. And that's our solution. If it had said to approximate it, we could plug this into a calculator to find the decimal approximation, but because it didn't, we'll just leave this exactly as we see it. Alright, from here we now have 5 to the x minus 3 minus 3 equals 122. Take a moment, pause the video, see if you can't work through this one. Okay, so trying this together, first thing we have to do is get this 5 to the x minus 3 by itself, so we'll add 3 to each side of the equation, giving us 5 to the x minus 3 equals 125. And now from here, there are a couple of ways that we could approach it. The first is we could take log base 5 of each side of the equation. But we don't have to go through it that way. This actually works out to be like our first type of equations that we were dealing with, where we could change 125 to 5 to the third power. But let's go ahead and stick with the process we just used. So we're going to take log base 5 of each side of the equation. Just a reminder, when we take log of each side of the equation, we are not multiplying by log, we're plugging each side into the logarithmic function. Okay, and when we do this, log base 5 of 5 will cancel out, leaving us with just x minus 3 equals log base 5 of 125. Well, log base 5 of 125, we can rewrite this as log base 5 of 5 to the third power. And now again, log base 5 of 5 will cancel out, leaving us with just 3. So x minus 3 equals 3. And adding 3 to each side of the equation, we get x equals 6. And we could do a quick check on that. If we plug 6 in for x, 6 minus 3 is 3. 5 to that third power is 125. Minus 3 gives us 122. Okay, so finally from here, before we move on to logarithmic equations, take a moment, try to solve this try to solve this problem, and just pause the video, and then we'll try it together. Okay, so from here, again, the first thing we need to do is start getting the exponential expression isolated. We'll do that by adding 5 to each side of the equation, which gives us 40e to the 2x minus 1 equals 120. We'll then divide each side by 40 to get that e to the 2x minus 1 by itself. So that gives us e to the 2x minus 1 equals 3. And now from here, to get rid of this base e, we have to take the natural log of each side of the equation. And when we take that natural log, the natural log of e will cancel out, leaving us with 2x minus 1 equals the natural log of 3. And from here, we will now solve for x by adding 1 to each side of the equation, giving us 2x equals the natural log of 3 plus 1. And finally, dividing each side by 2, which gives us x equals the natural log of 3 plus 1 all over 2. It's very tempting to want to add this 3 and 1 together and then divide by 2, but always remember this 3 is inside of that natural log. Everything else is on the outside of it, and treat the natural log like it's a square root. So if this were the square root of 3 plus 1 over 2, then you would know you can't simplify it. Think of the natural log the exact same way. This is as simplified as it'll get. And it's perfectly okay to put parentheses around that 3 if you prefer. I'm just leaving them out because it's one number, it doesn't need them. Okay, now let's move on to solving logarithmic equations. So the first type we'll start off with is solving a logarithmic equation of basically the form a equals log base b of m. It's going to be a very similar process. We need to start by isolating the logarithmic expression log base b of m. And then from there, we're going to raise each side of the problem by a base of b to get rid of that log base b. So when you take the inverse of each side of the equation, it's going to cancel out the log. Remember, you can also do this by just moving the base b to the other side of the equation, which gives us m equals b to the a power. Either one of these is perfectly acceptable to show your work. And once you do that, you will create a table to be sure that m is greater than 0 for all solutions. Okay, so basically everything was the same as exponential equations, except at the very end, we just have to make a check. Before, we would just do checks to see if we got the right answer. Now the check is actually required, as sometimes you will end up getting an answer that is not true. So let's go ahead and solve these problems. We have log base 4 of x plus 3 equals 2. So the first thing we need to do here is isolate the log. That's already done for us. We just have log base 4 on the left. So to get rid of this log, remember we move the base to the other side of the equation, which gives us x plus 3 equals 4 squared, which means x plus 3 equals 16. And now solving for x, we'll subtract 3 from each side to get x equals 13. Now before we circle this answer though, we have to do our check. So we'll make a table where we're checking x and we're checking anything that was inside of a log. In this case, x plus 3 was inside of a log. So we don't care if x is negative or 0. We care if the entire result of what's in the log is negative or 0, because if it is, then we would have an undefined answer. So we need to make sure x plus 3 is a positive number. So when we plug 13 in for x, we get 13 plus 3 is 16. That is greater than 0, so our answer checks out. X equals 13 solves this original logarithmic equation. Again, it'd be perfectly okay if x equals negative 5, for instance. What's not okay is if x plus 3, what was actually inside of the log, were negative 5. It has to be greater than 0. Okay, from here, this one's a little trickier, but take a moment, pause the video, see if you can't solve 2 natural log of 4x minus 3 equals negative 3. Okay, so trying this together, we're going to start by adding 5 to each side of the equation, which gives us 2 natural log of 4x equals positive 2. We'll then divide each side by 2 to get the natural log alone, which gives us the natural log of 4x equals 1. And now from here, we need to get rid of the natural logs, so we can either raise each side with a base of e, or we can just use our arrow method to show that we're moving the base to the other side, which gives us 4x equals e to the first power, or just 4x equals e. And finally, dividing each side by 4, we get x equals e over 4. And now we just have to make a table to prove that this worked out. So we're checking our x value, which is e over 4, and we're checking it in the value that was inside of our log, which is 4x. Remember, it did not say to approximate, so we will leave this as e over 4, its exact value. When we plug this into 4x, 4 times e over 4 is just e. And remember, e is approximately 2.7. That is greater than 0, so it does work out. X equals e over 4 is our solution. Okay, the last type of logarithmic equations that we deal with are when we have log base b of m equals log base b of n. So given any two logs of the same base equal to one another, then it must be true that m is equal to n. The n sides are equal to one another. As long as we make sure that m and n are greater than 0 for every solution. If they're not greater than 0 for every solution, then we omit the solutions that cause them to be less than or equal to 0. So with that, we have the natural log of x plus 2 minus the natural log of 4x plus 3 equals the natural log of 1 over x. Notice we have 3 logs here. This rule only works if you have 2 logs equal to one another. We can't drop these natural logs at this point because of this subtraction. This is the most common mistake with these problems. Commit to memory. It only works with 2 logs, no more. And there cannot be any addition or subtraction happening. Okay, so how can we get these 2 logs to be just 1 log? Well, remember, if we are subtracting 2 logs, then that means we can condense them. Subtraction becomes division inside of one log. So we get x plus 2 over 4x plus 3 equals the natural log of 1 over x. And now that we have two logs of the same base equal to one another, we can change the problem to just be the insides equal to one another. So x plus 2 over 4x plus 3 equals 1 over x. From here we have two fractions equal. Remember, you can always cross multiply when you have two fractions equal to one another. So that gives us x times x plus 2 equals 1 times 4x plus 3. We'll now go ahead and distribute the x and the 1, which gives us x squared plus 2x equals 4x plus 3. And now if we get everything to one side of the equation, we can factor and solve for x. So we'll subtract 4x from each side of the equation, which gives us x squared minus 2x equals 3. And then subtract 3 from each side of the equation to get x squared minus 2x minus 3 equals 0. And now we need to factor this such that we have two numbers that multiply to give us negative 3 and add up to give us negative 2. That'll factor into x minus 3 times x plus 1 equals 0. Negative 1 times 1 is negative 3. Negative 3, sorry, I said that wrong. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2, so it does end up working out. Okay, so from here we can now set each factor equal to 0. So we get x minus 3 equals 0 and x plus 1 equals 0. Adding 3 to each side and subtracting 1 from each side, we get x equals positive 3 and negative 1. Are these both our answers? Well, we have to make sure. Maybe neither of them are, maybe only one of them is, maybe both of them are. So we're checking negative 1 and positive 3, and what are we checking them in? X plus 2, 4x plus 3, and 1 over x. So the first one, when we plug negative 1 into it, we get negative 1 plus 2 is positive 1. That checks out. The second one, when we plug negative 1 into it, we get 4 times negative 1 is negative 4 plus 3 is negative 1. That does not work out. As soon as it fails one of them, it doesn't matter, it's automatically out. Negative 1 is no longer a solution. Now let's check 3. 3 plus 2 is 5. That works out. It's positive. 3 times 4 is 12, plus 3 is 15. That is positive. And finally, 1 over 3 is also positive. So our only solution is x equals 3. X equals negative 1 would cause the original problem to be undefined, so it does not work out. For our last problem, I'd like you to take a moment to pause the video and see if you can't solve this. We have log of 2x minus 1 equals log of x plus 3 plus log of 3. Trying this together, We are adding two logs together, which means we can condense them into multiplication, which will give us one log equals another of the same base, which is exactly what we need. So we get log of 2x minus 1 equals log of 3 times x plus 3. Now we can go ahead and multiply this 3 into the x plus 3. So we get log of 2x minus 1 equals log of 3x plus 9. And now we can set the insides of the logs equal to one another because we have two logs of the same base equal to one another. So we get 2x minus 1 equals 3x plus 9. And now to solve for x, we'll subtract 2x from each side of the equation, and then subtract 9 from each side of the equation to get the x's alone. You could spread this out into two separate steps if you prefer. And when we do that, on the left side we'll be left with negative 10, and on the right side we'll be left with just x. So x equals negative 10 is the answer we found, but remember, we have to make a table to check that. We're checking x equals negative 10 by plugging it into 2x minus 1, as well as x plus 3. But note, we don't have to plug it into the third log because that log is always going to have a 3 inside of it, which is always positive. Okay, so from here, plugging in negative 10 times 2 is negative 20, minus 1 is negative 21. This is less than 0. Remember, it has to be greater than 0, so it automatically fails, meaning there is no solution.